Hello everyone, myself Purva Joshi, Assistant Professor at Daiichi Institute of Engineering and Technology. Today we are going to study few more topics of sequence and series. So let's begin with the first topic, that is Cauchy's rule test. If series un is a series with positive terms and if limit n tends to infinite un raised to 1 upon n equals to L, then for L less than 1, series converges. For L greater than 1, series diverges. And for L equals to 1, the test fails. Okay, so whenever we have a series un with positive terms, and we will find this limit n tends to infinite un raised to 1 upon n. And answer is L. Okay, so if L is less than 1, the series is convergent. For L greater than 1, series is divergent. And for L is equal to 1, the test fails. Okay, so we will apply some another method. So if un is of the form bn raised to n, so for example, if we have un as 2 raised to n or n raised to n, right, any bn raised to n form, then we will apply this rule test. So let's begin with the example. Test the convergence of a series n from 2 to infinite 1 upon log n whole raised to n. Now here we are taking summation from 2 because for n is equal to 1, here we have 1 upon log 1, okay, and we know the answer of log 1, that is 0. So 1 upon 0, that is infinite. So for n is equal to 1, undefined term, right? So we will start the series from n is equal to 2. So now let's begin with the solution. Here un is given, that is 1 upon log n whole raised to n. Okay, so firstly we will find this un whole raised to 1 upon n, right? So now this n will get cancelled, so what remains is 1 upon log n. Okay, now we will apply limit. So limit n tends to infinite un raised to 1 upon n equals to limit n tends to infinite 1 upon log n. Okay, now as n tends to infinite, we have 1 upon log infinite. And we know the answer of log infinite, that is infinite. And 1 upon infinite equals to 0, which is less than 1. Okay, so by root test, we can say that this series un is convergent. Okay, one more example. Is the series n e raised to n convergent? So here un is given, that is n e raised to n. Okay, firstly we will find un raised to 1 upon n. So we have n e raised to n whole raised to 1 upon n. Okay, so first find out the limit, that is limit n tends to infinite un raised to 1 upon n equals to limit n tends to infinite n e raised to n whole raised to 1 upon n, right? Now this n will get cancelled and e we will take out of the limit. So we have e into limit n tends to infinite. From here we have n raised to 1 upon n. Okay, and we know this limit n tends to infinite n raised to 1 upon n equals to 1. Okay, so here we have e into 1, that is e, which is greater than 1. Okay, so we can say that by root test this series un is divergent. Okay, now one more example. Test the convergence of series 1 cube upon 3 plus 2 cube upon 3 square plus 3 cube upon 3 cube and so on. Okay, so here we have to find the un. Now you can see here the power 3 is fixed, but this number 1, 2, 3, 4 are changing, right? So we will write it as n cube. And here this 3 is fixed and this power, that is 1, 2, 3, this varies. So in place of 1, 2, 3, 4 in general, we will write 3 raised to n. Okay, so we have here we have un as n cube upon 3 raised to n. Now first we will find un raised to 1 upon n. Okay, so this is un, that is n cube upon 3 raised to n whole raised to 1 upon n. Now we will find limit. So limit n tends to infinite un raised to 1 upon n equals to limit n tends to infinite this term, right? Now this n will get cancelled from here and what we have is limit n tends to infinite n raised to 3 upon n upon 3. Okay, now we know the limit n tends to infinite n raised to 1 upon n equals to what? 1. So here we have 1. So on simplification you will get answer 1 by 3. Okay, now it is less than 1. So by root test, we can say that this series UN is convergent, right? Now, we will study the one more topic, that is alternating series. An infinite series with alternate positive and negative terms is called alternating series, right? For example, here we have 1 minus 1 upon 2 square plus 1 upon 3 square minus 1 upon 4 square and so on. Okay, so this we can write in general as series and from 1 to infinite minus 1 raised to n minus 1 into 1 upon n square. Now here you can see we have the negative, positive alternate terms, right? So this is an alternating series. Okay, so now let's study a method to solve the alternating series, which is known as Leibniz test. Okay, so the statement is, if the alternating series minus 1 raised to n minus 1 un, which we can write as u1 minus u2 plus u3 minus u4 and so on, where un is greater than 0. Okay, so if this alternating series satisfy the following conditions. The first one is mod un greater than mod un plus 1 for all n. Okay, so here we are taking mod, means we are taking only the positive terms of nth term and n plus 1 term. Okay, so firstly we have to show that mod un is greater than mod un plus 1 for all n. Next, we will show that limit n tends to infinite mod un is equal to 0. Okay, so if these two conditions are satisfied, then we can say that the given series is convergent by Leibniz test. Right? Now, let's begin with the example. So, test the convergence of the series minus 1 raised to n plus 1 upon log n plus 1. Okay, so from the question you can see that this is an alternating series. Why? Because here we have minus 1 raised to n plus 1 form. So if you will substitute n is equal to 1, 2, 3 and so on, so you will get the term as minus, plus and so on. Okay, so this given series is an alternating series. So we will apply Leibniz test. So firstly we will write down mod un. Okay, so we will just take the positive term. So we will write as 1 upon log n plus 1. Okay, now we will find this term, that is mod un minus mod un plus 1. So subtract this. Un we have mod un. So just write down mod un minus un plus 1. So in un, in place of n, just write down n plus 1. Okay. So here n plus 1 plus 1. So you have log n plus 2. Okay. Now just cross multiply this. So you will get log n plus 2 minus log n plus 1 upon log n plus 1 log n plus 2. Now we will see for n is equal to 1. Okay, suppose we have n is equal to 1, just substitute here. So you will get log 3 minus log 2. Okay, now and also in the denominator we have log 3 log 2. Okay, now this log 3 minus log 2, if you will subtract them, so it will always be greater than 0, right? So this term is greater than 0. So we can say that mod un is greater than un plus 1. So this is the first condition of Leibniz test. So we have satisfied this first condition. Okay, now next one, that is limit n tends to infinite mod un, that is limit n tends to infinite 1 upon log n plus 1. Now as n tends to infinite, here we have 1 upon log infinite, that is infinite. So 1 upon infinite, which we can write as 0. Okay, so limit n tends to infinite mod un is equal to 0. This is the second condition of Leibniz test, right? So both the conditions are satisfied, therefore we can say that the given series is convergent by Leibniz test. Okay, now we will solve one more example. Test the convergence of the series 1 minus 1 upon 2 root 2 plus 1 upon 3 root 3 minus 1 upon 4 root 4 and so on. Okay, so firstly we will find un. Also you can see that the given series is alternating because we have the minus plus terms. Okay, so firstly we will see that this is an alternating series and so we will apply Leibniz test. Now we will write the nth term. So given series is this. Okay, so in general we can write it as summation n from 1 to infinite minus 1 raised to n minus 1 into 1 upon. Now here you can write as 1 into root 1. Okay, so here we have 1, 2, 3 and 4 and so on, right? So we will write it as n. And here we have under root 1, under root 2, under root 3 and so on. So we will write it as under root n. Okay, now we will write firstly mod un. So mod un, so we will take only positive terms. So here we have 1 upon n root n. Firstly find mod un plus 1. So in place of n, here we have to write n plus 1. So you will get 1 upon n plus 1 under root n plus 1. Now the first condition, that is mod un minus mod un plus 1. Subtract both the terms. Okay, now suppose we will check for n is equal to 1. So here we have 1 upon 1 under root 1 minus 1 upon 2 under root 2. Okay, now this is 1. So 1 minus 1 upon 2 under root 2. This is greater than 0. Okay, so we can say that mod un is greater than mod un plus 1. This is the first condition of Leibniz test. This we have satisfied. Now the another condition, that is limit n tends to infinite un equals to limit n tends to infinite 1 upon n under root n. Now as n tends to infinite, here we have 1 upon infinite, that is 0. So which is the second condition. So limit n tends to infinite un is equal to 0. And both the conditions are satisfied. So we can say by Leibniz test that the given series is convergent. Okay. So in all, what we have studied first, root test. So here first we will find limit n tends to infinite un raised to 1 upon n. Okay, and this answer is L. So if L is less than 1, so the given series is convergent. For L greater than 1, the given series is divergent, and for L is equal to 1, test fails. Okay, so we will apply some other test. Next we studied alternating series. Now here what we have, series of the form minus 1 raised to n minus 1 un. So here the terms are alternating plus and minus, right? So the series are known as alternating series. And to solve the alternating series, we will use Leibniz test. Okay, so in this test, firstly we will find mod un minus mod un plus 1. Okay, and this should be greater than 0. And the second condition is limit n tends to infinite mod un is equal to 0. Okay, so if these two conditions are satisfied, then we can say that the given series, that is alternating series, is convergent. Okay, so I hope you have understood in this session. Thank you for watching.